Hello, I am Dr. Ali Mohammadi, a lecturer in the Department of Electronic and Electrical Engineering, University of Bath. I teach the first half of Sensors and Instrumentation unit over the last few years, which is specifically developed for our Master's Mechatronics students. This is one of the 5 units in the second semester of this one-year program. Here I have provided a brief outline about the unit content and its learning outcomes. I hope that you find it useful. In a typical mechatronic system, we use sensors and controllers in a closed-loop feedback system to improve the precision and accuracy of the system output. For example, a car crash system consists of accelerometers that detect sudden changes in acceleration caused by crash in a very short time and activate the vehicle airbags, which saves the passenger's life in disastrous car accidents. Our unit will focus on the transducers that are used as sensors and actuators, particularly in micrometer dimensions, such as accelerometers in this example. Therefore, we will start by introducing the microfabrication processes used to make different transducers. We will discuss different transduction mechanisms, such as piezoelectric, electrostatic or capacitive, and electrothermal sensors and actuators, with real-world applications in microelectromechanical systems or MEMS. We will also investigate cutting-edge research work being carried out on these transducers. For example, we discuss atomic force microscopy on a chip, programmable magnetic transducers, and microenergy harvesting applications. In the next few slides, I will show microscopic images and videos recorded from our ongoing research in MEMS. The signals recorded from microtransducers are very small, in the range of microvolts and nanoamperes. In the second part of this unit, we will learn the signal conditioning interface electronic circuits, such as amplifiers, filters, and analog-to-digital converters required to process the output of these sensors. Therefore, the unit lectures are designed in 2 parts. In the first part, we introduce the transducers. We discuss the microfabrication processes used for making these sensors and micromechanical rules that govern the operation of the transducers. We also study the most popular transducers, including piezoelectric, piezoresistive, capacitive, and electrothermal devices. In all mechatronic systems, interface electronic circuits are required to amplify and enhance the recorded signal from sensors and make it available for the following signal processing and control steps. So in the second part of this unit, the readout and conditioning circuits, including amplifiers, filters, and A to D converters and PLLs are discussed. Microfabrication skills and equipment required for making integrated electronic components and microelectromechanical devices in clean rooms are usually expensive processes for prototyping, though there is a cheaper way of running research and development in microfabrication, and that is Fabless approach. So in Fabless approach, we design and simulate the micro devices using commercially available process technology files in CAD tools. So we introduce basically CAD tools here in this unit. We outsource the microfabrication phases of these projects, and we run in-house measurement and characterization steps. So example microfabrication processes are MOMS, InvenSense, and Tronics Harm. We start by reviewing the photolithography process, which is the common approach to make micro devices on semiconductor substrates. This is followed by introducing some commercially available microfabrication process technologies, such as MUMP and XFAB technologies. For example, this image is the cross-section of piezo MUMP process, where piezoelectric layer is sandwiched between 2 conductive electrodes. By designing a 2-dimensional layout of the device, we make 3D microstructures to be used as sensors and actuators all integrated on a silicon substrate, as shown here with the blue color. Although countless sensors are developed and used over the years, but only a few of these have higher chances of being integrated in microfabrication processes. For example, in this slide on the right, the operation principle of electrothermal actuator is demonstrated, where applying electric power to a resistive silicon beam causes longitudinal expansion, which is extremely small. Displacement amplification by chevron-shaped transducer amplifies the displacement of shuttle at the middle. The CAD simulation shows temperature distribution all over the actuator in response to applying electric power to the pads. This video here shows a chevron actuator that is used to generate on-chip mechanical impact. So you can see the moving shuttle at the middle in response to an applied electric sinusoidal voltage. Atomic force microscopy as another example, which is patented in 1986 by physicist Nobel winner Gerd Binning, is still an enabling microscopy technique that offers 1,000 times higher resolution than strongest optical microscope. So the operation principle is absolutely simple here. So if we put the sample on a scan table that can move in X and Y directions, as shown in this image, so in a planar directions, and allow a microcantilever beam scan the surface of sample, based on the reaction force of the beam, we can find the Z coordinate of every point. The processor or computer can sort these X, Y, Z coordinates and generate a surface image of the sample. The imaging speed of existing devices are limited by the mechanical resonance frequency of mesoscale actuators. So you can see the very large dimensions of this commercially available tabletop AFM, which is limited in scanning speed, and it's also very costly. So using a microscale electrostatic actuator that could move much faster is the solution to this bottleneck. In addition, by integrating electrothermal displacements and microsensors in closed-loop control system, we improve the displacement measurement accuracy up to sub-nanometers. So you can see a closed-loop control system here, where there is a stage, a scan table, which can move in one direction only here by electrostatic actuators, and displacement can be measured by electrothermal sensors, which are extremely small. This slide shows the magnified image of electrostatically actuated XY scan table and integrated electrothermal sensors, all built on silicon and using commercially available silicon on insulator microfabrication processes. Here we use the cantilever beam of a commercial tabletop AFM to tap on the surface of the samples, which is the gold features we initially built on the scan table to test our design. Our XY nanopositioner scan table is located underneath the beam, and the images on the right are generated on the computer screen using this scan table. The closed-loop system achieved by integrated electrothermal sensors improve the quality of images, especially at high scan speeds. So when we increase the scan speed from 10 Hz to 50 Hz and 100 Hz, in an open loop system, we lose the quality of image, whereas in closed loop system, using the integrated sensors, we can improve and enhance the quality of images. Here is a video of 1 degree of freedom electrostatically actuated scan table, and it's microchip packaged and soldered on the PCB on the right side of the image. So you can see the left-right movements of the stage, and this is a magnified image where electrothermal sensor is there to measure the displacements of this 1DOF stage. Further research has been progressed on this prototype by integrating cantilever beam in the same, the Z beam in the same microfabrication process by my colleagues at University of Texas, Dallas. So that was one practical example of an advanced mechatronics system.